It's a pleasure to be with you today and to share with you some of the equipment that I've had the privilege of working with for the last many years, on using it on consulting projects and things of that nature. This is going to be very fast-paced because we're going to try to cover 4 materials. What I will do is probably leave much of the demonstrations for afterwards so that you can all gather around here and see it as we're doing the presentation. The first one we're going to talk about is infrared thermometers. And infrared thermometers is a technology that many of us are familiar with in some way, shape, and form. What it does is basically collects energy from an object. Anything that is above absolute zero gives off radiation. So what it does is captures that. It follows the same technology if you have done any welding or use a torch. You could probably recognize these. You can look at the material as you are cutting it or as you are welding it and get a good approximation of what the temperature of that material is. And this just shows you some of those looking at it. These are what you can see with the eye. Now the infrared takes us to the areas that we cannot see with our eyes. The infrared is not part of the visible spectrum. The visible spectrum is shown up there. But what it does, it gathers that information so that we can do it. And again, it collects all the energy from that. The radiation is coming off of that, and then it converts it. There's a little computer in there, if you will, that converts that energy that is captured and gives you the temperature of the material. This is what the equipment looks like. These are 2 different types of equipment that you might see by 2 different manufacturers. And it's a very simple piece of equipment that you can use. There's some limitations of using the equipment are that you have to be fairly close to the equipment. And that what this is saying is if it's an object that is 1 centimeter wide, you have to be within 8 centimeters of taking the shot. So you cannot use this, for example, to take the temperature of the sun. It's obviously way too far away from us to get that. So you have to be fairly close to it. There is a laser sighting on it. And I'll just show you one of the pieces of equipment. This is what it looks like. And if you look over here, you can see there's a laser that's with it. The laser is very important only in that it identifies the object that we are taking the temperature from. It has no basis or no input into the calculation itself. So it's only useful in identifying the object that we are taking the temperature. Here is the typical information that you get from this. The particular ones that I am showing you will have a temperature range of 20 to 300 C, and it will be accurate to about 1.5 C. I have 2 of the pieces of equipment here. I was checking them right before the presentation. The variation on the equipment is about a half a degree. So that gives you an idea of how it works. It's got typical battery power. And you can, if you want to take it to the United States, you can actually use it on the Fahrenheit scale as well. There are some limitations. We've already talked about one, that you have to be fairly close to it. But what is very important, all it does is measure your surface temperature. So if I was to take my temperature, say, of my arm, I get a reading of 30.9, which would mean if I was in the hospital and they took my temperature, that means I'm basically dead. What it's doing, though, is measuring just the surface temperature of my arm. When the medical doctor takes my temperature, he sticks something in my ear, under my tongue, or in some hospitals, the plate where we don't want to talk about, I'm just glad that they don't use something like this when they're doing the temperature in the hospitals. So it measures only the surface temperature, and that's very important for us to realize. We cannot shoot through a window. We can't stay in our car and shoot at an object through the window. We're going to get the temperature of the window itself. It does have a laser in it. So again, you have to be a little bit careful. You don't want to shine the laser in somebody's eye. And you cannot use it if there's a lot of rain, dust, smoke, or things of that nature, because it's going to be measuring the temperature of the particles in the air. So what can we use it for? Well, it has several uses. We can measure, in our construction area, we can measure the forms and the reinforcement. In ACI documents, it says that all embedded materials should be less than 50 C. Now, I live in Arizona, which is a desert. Very hot temperatures, we will get up to 50 C in our area. And unlike Singapore, we have very often our humidity is less than 10%. So again, it's quite a bit different. And if you get into your car in our area, many times the car will be 60, 65, 70 C just because of the heat buildup. And you'll see the same thing happening in construction, that the steel forms or the steel embedments will be very hot. We can use it to estimate the concrete temperatures during the placements. And again, on many specifications, we have to keep the temperatures above 4 and below 35. We can also use it for temperature control. We can determine the measure of the mixture and maintain it during the curing. And we can also use it to determine the concrete temperature to get a good estimate. Now, if we're doing this on an official basis, following a procedure, we have to stick the thermometer in 75 millimeters, tap around it to make sure that it's seated, wait for 2 minutes. What we did is a research project where we looked at where can we do this and get the same temperature that is many times required on a job site. We looked at the 3 areas, and what we found as the concrete is coming onto the chute, if you take the temperature of that concrete, it is a very accurate estimate and very similar to the required temperatures that we might take. We can use it to determine the concrete temperatures of a mixture. And this formula is a very common formula that you'll see in many of our concrete textbooks. It tells us that if we know the mass of the materials and the temperature of each materials, we can do that. So if we get the temperature of the cement, the measure of the temperatures of the coarse aggregate, the temperatures of the fine aggregates, we can put it into this equation and actually calculate it. And here is an example of how you might use it. Here is your mix design, and here's the temperatures of each one of the materials as we put it in there. And if we do that, the temperature of the concrete must be the temperature of the concrete is 38 degrees. So if we're going to have to keep it below 35, maybe by specifications, we can back calculate, and I have a computer program if anyone is interested, and I will leave that with the chapter if you would like to use this computer program. And it's copyable. It's something we did as a research project at the university, so we make it available to the public. We would have to chill that water down to 24 C if we're going to maintain that 35-degree temperatures. And the way we would get these temperatures is by using the infrared gun to determine that as we are, before we put the materials into the concrete. So, to give us a kind of a quick idea of what we can do with the infrared. We can use it to monitor the temperature of the concrete without interfering with the placement. Again, if you are going to do the official test, you've got to get a sample, you got to get it in your wheelbarrow. That means you are diverting the work. and diverting the concrete into the chute itself, interrupting the work. So if we use the infrared, we can do every truckload of concrete, especially when it's really hot. If we have an upper limit on the concrete, we can check every load and then be able to get information back to the batch plant that we may have to do some corrections on this if it's possible. We could use it to measure the embedded items that are in the concrete and the formwork itself, and we can monitor the stockpiles and determine the temperatures of that material. So, if you will, we have the equipment up here. There's to be available at the end of this session for you to come and take a look at it. I would assume some of you are very familiar with it. In the United States, we use this a lot in asphalt construction as well. We can actually determine where a pothole will form, because the asphalt, the lower the temperature of the asphalt, the less compaction you're going to get, and that will be an area that will be problematic. Our second part of the talk we're going to do is we're going to talk about preventing plastic shrinkage cracking. Again, this is a serious problem in a very dry area. Saudi Arabia, my home state, Arizona, we live with this problem as a constant problem that we might have to deal with. And what plastic shrinkage cracking is cracking that occurs when the rate of evaporation is greater than the bleed water of the recently placed concrete. In essence, what is happening, the evaporation rate, because it's very hot or windy or low humidity, the water is being ripped out of the concrete. And when it's ripped out of the concrete, the end result is cracking. You may be familiar with it if you look at a mud puddle. This is an example of it drying out after a rain, if you will. You can see the cracks that occur in that. In concrete, this is what it would look like. These are cracks. They tend to be, if the wind is blowing, you can see where the wind has been blowing on that. They are very problematic in some areas. They tend not to interfere with the structural aspect of it, but if this where seawater is, or where you have cold weather, water can get in that and work it and cause more damage to the crack, open up the crack even more. And if it's seawater, that would be a place where seawater can get to the rebar. And then you can lead to corrosion issues as well. Another examples of it, of plastic shrinkage crack, just as on a roadway. Now, I've done a lot of work on this particular one, and I've developed a computer program that is, again, available for you if you would like a copy of that. And there is a graph that is given in ACI 305 and 308 that is very helpful. Now, the graph is old technology. What I'm going to show you is research work that was done in the early 1800s. And the work was done to determine the evaporation rate off of lakes. In 1940, some people at the National Ready Mix in the US found this and said, water on lakes is very similar to water on concrete. So we can use this particular one. Now, this is back in 1940s when we did not have a lot of computer programs. I didn't have computer programs. We did all our work by slide rules. And for many of you who may have collected old engineering books, we had a lot of charts and graphs to make it much more simpler for the engineer to use. And that's what this technology is. And what it does is says there's a relationship between the evaporation and the concrete temperature, air temperature, humidity, and wind velocity. So if we know those, we can actually calculate the rate. And they give you this graph. And this graph is, again, not something that most engineers of today are used to using. So we'll go through kind of a quick example. We took and got that information. I got an air temperature of 25 C, humidity of 97, concrete temperature of 30, and a wind velocity of 20. So what we will do is we will enter the graph at 25, and we will go up to the relative humidity of 90, and then we will go over to the concrete temperature of 30, and then we will drop down to the wind velocity, and then we'll go over here and read, and it's the scale just a slightly off because of the PowerPoint, but that value turns out to be 0.49 kilograms per meter squared per hour. So what does that mean? Well, what we have found is if it's above 0.1, or 1 kilogram per meter squared per hour, plastic shrinkage cracks are going to happen. You can almost predict it. If it's between 0.5 and 1, it may or may not happen. It just depends on how lucky you are that day. If it's below 0.5, they're likely not to occur. And you can almost predict that they will not occur. On ours, because it's 0.9, we are in a safe zone. So we will not have to worry about whether we're going to have plastic shrinkage cracks. Now, we have solved one issue in that we can now determine whether we can get plastic shrinkage cracks. But the second problem is, how do we get that information? Where do we get wind velocities? Where do we get concrete temperatures, air temperatures, and relative humidity? Well, I've gone on many cases, and as a young engineer, I got called in on many of these cases of cracked concrete. How do we get the information? Well, the information after the concrete is already placed is already cracked. So that's not very helpful if I'm a contractor or I'm a ready-mix supplier, because I'm going to get blamed for the concrete if I'm a ready-mix supplier. If I'm the contractor, I'm going to maybe even have to replace concrete. I recently worked on an airport where they had some plastic shrinkage cracks, and whole slabs had to be removed because a contractor did not pay attention to the weather conditions. So where do we get that information? Well, when I started in this, I would go to the local airport information that's published in newspapers and things like that and collect that information. If that's all you have, that's probably the best you're going to be able to do. But if I'm a contractor, this information is not going to be very helpful. Number one, especially in the United States, probably not so much of a problem here in Singapore, but in the United States, the airport may be 100 kilometers from where I'm doing the construction job. So that information is not going to be very helpful for me. Also, what we find, and I think it's, I don't have a slide on that, but when they do it at the airport pilots, or the pilots that are landing the planes, they care about what the wind is at 10 meters. And that's where they measure it at the airports, because when they're landing the plane, we've lost some planes that had actually crashed by what we call wind shear. Also, if you're working in downtown Singapore, as wind is coming around buildings, you get these eddy currents as the wind's whipping around. What may be happening at the airport, which is open, is going to be quite different than it is as wind's whipping around buildings. So we have to get the information as close to where we're doing the concrete as possible. And the chart, if you read the chart and information on the chart, they say I'm supposed to measure the air and humidity roughly 450 millimeters above where I'm placing the concrete. And the wind, it should be the average, and that should be 1,200 millimeters above the placement. So how do I get that information? Well, that's where this type of equipment, what we call a handheld weather station, comes into play. This is a particular one. By the way, many people who do competition shooting with rifles and handguns will use things like this. For people who are doing sailing or skiing, they might be using equipment like this. This temperature, this particular one, gives me the air temperature. It just gave me the wind chill, which is not very important here in Singapore. Relative humidity. Relative humidity in this room is right now about 59%. I have this set on US, and the hot air up here is about 7 kilometers per hour. So you can see a little fan in there. A little fan allows me to measure the wind speed. This right here is where I measure the relative humidity. So this is something that I can use and set up very quickly, determine what is happening immediately above where I am placing the concrete. So this can be of great help to me to be able to do that type of analysis. We did a research project on this as well, and I had grad students working on this particular problem. We set up a approved weather station, and I'll show you that in just a minute. We took over 150 readings over about a 6-month period, and we were looking at several pieces of equipment. These are my grad students, and this is a grad student from Mongolia. This is a grad student from Pakistan. And this is the weather station that they had. This is approved. You can see where the weather, although this is probably taken a little bit higher than where we were taking the readings. You can see he has 2 pieces of equipment there, and she has 2 pieces of equipment that we are using. There are several pieces of equipment that are available that does, and if you just type in handheld weather station in Google or Yahoo or whatever your search engine you are using, you will find them. What we found is all of these pieces of equipment work very well and very accurately. I particularly like this piece of equipment that I showed you just because it is easier to use. Some of these other pieces of equipment, you had to push 2 buttons at the same time and things of that nature. And if you don't use it every day, it becomes very cumbersome to try to figure out how to use that piece of equipment. Found all to be accurate, and we made the decision based on which we thought was the easiest to use. Now these are some, we have used this. We do a lot of airport construction in our area, and these are being done in our area. We do most of our concrete work at night. We get up over 50 C temperature in our area. So at night, it actually cools down to maybe 35 C. This is, again, taken at night while we're doing some airport work, and this is probably done in the winter months because we're actually doing some of that during the daytime. You can see the paving operations. The critical times is when the concrete is warm, or I will say when the concrete is hot, when the concrete is above 30 Celsius. When we have low humidity, again, not a very common problem in your area, but again, we get a lot of our areas. I've actually seen it in our area where the relative humidity is about 2%. And that is very difficult time when it's windy and we have hot days. Those are all the type of things, but anything that you can see that has to do with increasing the evaporation is going to be bad for the concrete. Now I'm going to stop for just a minute so that our fellow that's taking our video recording of this can reach up, change the tapes. So,
30 more minutes.
huh?
I have 30 more minutes on this tape.
Okay, so we go ahead. Okay. I have a chart, and I'll show you the chart. I'm going to do that at the last part of this, where we could actually use this. And the beauty of what I'm going to show you is we can do a what if. So I can put in all the information and then say, okay, we got a bad situation. What do I have to do with the concrete temperature? Or do I have to wait later in the day when it cools down a little bit? Or wait for the wind to drop, and how far does the wind have to drop before I can place concrete? So the idea of this is to make it very much more easier for the contractor to make a decision. Not to use it after the concrete is already cracked, and now we're trying to figure out who's going to pay for the cracked concrete, but to use it to prevent it from cracking and only placing concrete when we have conditions that are ideal to prevent the cracking. The third piece of equipment we're going to talk about is the electronic metal locating devices. Now, there are many of them out there, and if you go onto your websites, you will see many of them. I'm going to talk about one in particular that is of lower cost. Well, why do we need to worry about rebar anyway? Many of us get involved in concrete work where we have to take cores because we had an issue with the concrete. Well, if we're going to take cores or we're going to drill a hole into concrete, the last thing we want to do is to hit the rebar. So if we can find a way of not hitting the rebar with a piece of equipment that is relatively easy to use, that would be very beneficial to us. ASTM C42, which is the code we use in the United States, that talks about how to take cores. It says avoid embedded rebars, and thus we need to determine where the rebars are and to find safe locations. Again, there are several pieces of equipment that are out there. These pieces of equipment are ideal for doing this type of work. The problem with this is they also are very expensive. These would not be the type of equipment you would send out with a coring crew because they're very expensive and they may get damaged during that process. So what we did, and we actually did some studies on this, we were looking at, is there equipment out there that is relatively simple to use and inexpensive and is accurate in finding the equipment? And what we found out, yes, there is out there, but there's going to be some problems. This is a tilled up project, and I don't know if tilled up is a very commonly used here. In the United States, we would pour the concrete slab, and then we would pour on top of that the concrete that we would then lift up to be the wall. And thus, we have a lot less forming issues on that. But we had to put in more steel. And because we're putting in more steel, it becomes very difficult to locate it when we have lots and lots of steel in there. We also, if you are using a piece of equipment, there are many places where we have steel in there that is not continuous. Now, if this is a concrete floor, we can pretty well know there's going to be steel running this way and there's going to be steel running this way. So knowing that and knowing that the steel is continuous, we can use that. So what we would do is we may scan this way 2 meters from the wall to find where the rebars are, and then go another 2 meters, then another 2 meters, and put chalk marks on the floor. If it's a rebar, it will be continuous. If there's an area right here that I get a reading, that may be where someone dropped some nails in the concrete, or maybe there's a tin can there. There may be lots of reasons why there is a piece of steel in a particular area that is not a rebar. So you got to be able to trace the rebar itself. The equipment, first thing you got to do if you're going to do this, you got to remove all the dust and debris from the floor. You got to have a clean floor to start out. You have both an audible and a silent mode. I don't recommend using the audible. If you're using that, it'll get very distracting to you because you'll hear beeps all the time. And when I use the equipment, I turn it off and I spend my time looking at that equipment. And what you will see, and this is one of the pieces of equipment we're going to be talking about, you'll actually see as you approach it that it will start showing a plus sign. And if you got a scale here, and when you get right over the rebar, you will see that if you have the sound on, it will beep. And if you don't have the sound on, you'll see a maximum reading. And then as you start to move away from it, it will go from a plus sign to a negative sign. So you can very easily determine when you are over the rebar. And it would also give you a reading of the depth of the cover. So the way I would recommend that you do it is you use chalk marks. Again, move every 2 meters and put that down. This shows you how we developed a pattern. So we went every 2 meters, put that down, and then we went the other way, and we found the dotted black lines show the rebar locations. So if we are going to take cores, we know, for example, right there is a good place to take a core because there is no rebar in those areas. So again, we've got a way of isolating where it is safe to take, or in another way of saying it, where the rebars are not. So we again did a study in our laboratory. And what we did is we used different size rebars. I put spacers on that. You have to get this up high enough and away from all metals. The first time I did this, I had my students go to my office and I said, grab some of the magazines. It doesn't make any difference whether it's magazines or concrete, or it's just measuring the distance between the rebar and where you are. They got a whole bunch of magazines that had staples holding them together. And when we did the scanning, we couldn't make it work. Well, it was identifying where the staples were in the magazine that was holding it together. Concrete International, this is an American Concrete Institute group, their magazines are glued together. There's no staple in there. So I would recommend, if you're doing a study like this, that you use Concrete International magazines. And so we put those on there, and then they did the scanning. This shows them doing it with a bigger piece of rebar. And here is the experimental data. This is done in the US, so we had a number 4 bar, which translates to a 13 millimeter. And you can see that when we scanned it, we were within 12 millimeters, both this way, scanning it, be able to locate the rebar, and that with the rebar was stationed at 25 centimeters, or millimeters, excuse me, and it gave me a reading of 20, and you can see the data down there, the ones in parentheses. That's for a number 13 rebar. For a number 6 rebar, or a 19 millimeter, or probably you would say 20 millimeter, you can see it was almost dead on, and that's what it's calibrated for. And then for a number 32 rebar, you can see it gives a little bit higher readings because there's a bigger mass in it. You cannot dial in a different size of rebar. All it does, it tells us where the location of it is, and you can see all of them were within 12 centimeters, or 12 millimeters of location from this way, and the depth was pretty well dead on all of the locations. I was doing some projects over in Mongolia and working with some of the students in Mongolia. And this shows location of finding areas that are safe location of areas. And this is a field study where they were finding the location of steel in pipes and finding steels in them. Now, again, speaking just real bluntly, if I was doing a consulting job, and let's say we had pre-stressed cable in there, I would probably use a much more sophisticated piece of equipment. Ground penetrating radar, using some of the more expensive cover meters, because as you saw here, it was, was within 12 millimeters, and the last thing you want to do is hit a post-tension cable. So I would probably use a much more sophisticated piece of equipment. But for a typical construction rebar, where I'm trying to make sure I avoid where the rebar is, I find this is a good piece of equipment and one that I can easily train a crew on how to use. So it's accurate within, the company says it's accurate within 25 centimeters or 1 inch. And we found that very much it was really a lot more accurate than they claimed it to be. And suitable for finding locations. Well, as we were working on this, we found that there was some need for some other equipment, and many people will even want a easier to use piece of equipment because what they're trying to do is a much simpler type of thing. As an example, if I am doing a masonry wall, I may want to just do a quick check, did they put the steel in there? Or if this got a masonry wall again, they got horizontal joints, are the steel in the joints? So there is another piece of equipment that was out there, and we was doing some investigation on that. The company asked me, is this equipment easy enough to use so that people that are not familiar with using this type of equipment and international people that may not have English as a first language, would they be able to use this piece of equipment? So we went over and did a study while we were in Ethiopia. We were starting the ACI chapter there. And so I worked with some of the students there. And the students were ideal because most of the students, unlike people who work in construction that are used to using tools, they are not. So they were ideal of how to do it. So what we did, they had a DVD. The company provided a DVD, and we just gave them the equipment and said, here's the DVD, and here is the written instructions. You know what? Not one student looked at the written instructions. They all watched the DVD. So that's kind of typical of today's students as well. And you can see they're looking at it. That poor guy is not getting it. The rest of them seem to be getting it pretty well. And then we had some prepared samples. And this sample as a rebar is off center, so we could turn the sample over and be able to check it. Here's the piece of equipment we're looking at. This piece of equipment, very inexpensive. In the US dollars, this is less than $40. And very simple to use. You just push the button and you just scan. This one does give a beep, and when you're right over the rebar, it lights up. And you can watch that. Very, very simple to use. And here they are, they're doing it. And the students were able to find the rebar quite easily. We then had them go to some columns. Columns are very easy to use to find the rebar because we know where the steel is going to be in the columns. They're going to be basically close to the edges. So they were able to find them as well. And you can see this guy, I think that was the guy that was very concerned in the beginning. Now he's getting it. So what we found is by just following the DVD, going through it a couple of times without any written instructions, without me explaining through a long lecture to them how the equipment works, they were able to do it. They were able to find 10, 15, and 30 millimeter bars quite easily. The 10 millimeter bars they could find to a depth of about 65 millimeter. The 15 and 30, they could go to about 75 millimeter depth. So it does have a limitation. It's not going to find the deep steel. It's not going to find the bottom steel of a beam, for example. You might be able to scan it from the bottom side of it and find it. But again, it's not going to tell you depth. It's going to just going to be able to tell you it is there. And so we found it with the students when they were doing this, they were able to locate the reinforcement columns. It was logical, and it was a very simple piece of a tool to use. Has great use if you got a very simple application. So I would recommend that piece of equipment if you're going to do it. And there are some other areas where this is important. In the U.S., on flooring, we have to install moisture probes. Moisture probes, we got to be very careful we don't hit steel. And when we're using the other piece of equipment that I'm going to show you, the rebound hammer. The rebound hammer, we got to keep, again, this is a U.S. Requirement, is 3/4 of an inch, which translates to 19, you might as well say 20 millimeter, to keep it away from any reinforcement as we're doing that type of testing. So those type of equipment has some great uses, very simple, very inexpensive, and it has a great use if you're doing a very detailed engineering investigation where location of steel is critical. I would recommend using some of the other pieces of equipment. Last piece of equipment I'm going to talk about is the rebound hammer. And the rebound hammer has a good reputation and an awful reputation. And part of the reason we'll go through this, why people love it and why people hate it. And the rebound hammer is a non-destructive testing technique in particular. And what is the definition of non-destructive? This is the definition I wrote. I like this, so you won't find this in any textbooks unless you're reading some of my work. But it's the measurement of a property that is easy to measure to estimate a property that's more difficult to measure. Now, if you stop and think about it, a lot of this equipment that we're talking about, we are not measuring exact what we are trying to do. If you look at the infrared, we're measuring radiation energy off it. We don't want to know the radiation energy, we want to know the temperature. When we're using these type of equipment, some of this equipment are magnetic, and thus those type of equipment, we're measuring a flux difference or an eddy current difference. We don't care about that. We want to know the depth or the size of the rebar. And so that's what I'm getting at right here. In the rebound hammer, what we want is the strength of the concrete. So we're using an indirect measurement to determine the strength of the concrete. It is also a testing that does not physically damage the structure. So if I take a core, the core does some physical damage to the concrete. It's got to be repaired. This is a technique that is not needing to be repaired. Some of you may be familiar with some of the other non-destructive testing methods that we use. Windsor probe, where we shoot a dart into the concrete, or ultrasonics, where we put sound waves through the concrete. Again, all of these are measuring properties that if you had the right equipment, we can measure it, but that's not what we want. We want to use that to estimate strength. Well, why is non-destructive testing not an exact science? Well, part of that reason is concrete itself is not an exact material, in that we put together cement, coarse aggregate, fine aggregate, chemicals, water, and it is not going to be exactly the same all the way through. Concrete surface tends to dry out, where the interior of the concrete remains wet. As a graduate student, I was working on a project where I was looking at some 50-year-old concrete. And we were using some cutting torches near it, and the concrete was hissing and popping. There was still, after 50 years, moisture in the interior of the concrete that was now being turned to steam and blowing off the part of the concrete. So that concrete is going to stay wet for a long period of time. And the third part, every piece of equipment is going to be quite a little bit different. So there's going to be variations in the equipment. Well, the rebound hammer, some of you may know it by other names. And part of the reason it was developed in 1948 by Dr. Ernest Schmidt, a research scientist that now is part of one of the companies that makes the equipment. And thus we call it the Swiss hammer because he was a Swiss engineer, or the Schmidt hammer because that's his last name. Or if you want to keep away from those, you use the concrete test hammer or rebound hammer or surface hardness. There are several of these out there. Virtually all concrete companies have them. Many ready-mix plants have them. Most testing laboratories have them. In the United States, just about everyone that sells concrete products, the cement companies, the admixture companies have these. So there's more than 100,000 of them. It is so popular, you can buy them on eBay and get them through the internet. You can pay as low as $250, this is US dollars, up to about $2,500 for some of the more sophisticated pieces of equipment. We have them where you can have it actually connect to your computer. There's also some equipment out there, very sophisticated in their design, in that the equipment is designed in such a way that it stores all the equipment and all the information that comes out of that and gives you exact numbers of strength of the concrete afterwards. What this rebound hammer really measures is the surface hardness of the concrete. It has virtually nothing to do with the strength. Now, there's no theoretical relationship, so we cannot defend using the rebound hammer by showing a mathematical equation of how the concrete works. Now, I'm going to go do a quick demonstration. I'm going to show you the poor man's rebound hammer. This is a golf ball. And if I'm holding this up, I'm holding it up, about 1.75 meters. If I drop it, for those up front, you saw it bounced back about that high. That is the whole theory. What we are doing is we are taking a rebound, the rebound hammer, it's got a plunger in it. We are hitting the concrete and seeing how much it bounces back. So that's the theory. And I'm going to show you, this is the rebound hammer. This is now ready to be used. So I got to get it ready. It's now in the process, excuse me. To use this, I'll do it over here on this. So what I would do is push it. I'm not going to do it because I don't want to do any damage to that. But I would push this in. There is a reading right here that would be 2025. Now, what do I do with the 20 or 25? And that becomes the second part of what we're going to talk about. We get a reading, a rebound hammer. For some of you who have used that, you will see on the back of this, there is a chart that says a rebound number of 25 correlates to a certain strength of concrete. But if you stop and realize this, that this value is a general value. It depends on the rock that you are using in your concrete, your coarse aggregate. And I'll show you a slide that shows that variation. But if you think about this, if I'm talking about rock that's here in Singapore, that may be entirely different than the rock that's in North America, that is entirely different than the rock that's in Europe. So we got to be very careful when we start using a graph like this. As a matter of fact, what I would encourage if you're ever doing this is to do it with your local aggregates and your local mix designs. As a matter of fact, that's a requirement as we are doing this and what they encourage us to do. But what we have found out, and using this equipment, that a low number, say below 20, indicates that that surface is soft. Now, for those of you who do golfing, or if I take the golf ball and drop it on a steel plate, it bounces up almost as high as I dropped it from. If I drop it on something that's really soft, it absorbs the energy and it doesn't bounce very high. So that indicates a soft surface, and a soft surface basically tells us we have a weak concrete. If I get a high number, that means I have a hard surface and I have a strong concrete. So that's kind of all the theory we have to go on and why the rebound hammer works. Now, if we're using this, we got to recognize that we got several things we have to be concerned about. First off, if we have a hard spot or a rebar that's very close to the surface, if I hit that with a rebound hammer, I'm going to get a very high number. If I look to the area where I have honeycomb concrete or a void in the concrete, I'm going to get a low number. These could be right side by side. Now you get an idea of why people don't like it. Because I can go and do a study. If I look for all the areas that have a tough surface or rebar close to the surface, I'm going to get entirely different than if I look for the areas that have voids in it. So again, that's one of the problems we have. If I have an irregular surface where it's rough, who knows what I get? I may get a high value, I may get a low value, because it just depends on how I'm hitting that surface. So when I'm doing this, and the equipment, they didn't bring that part of it, but there's a little grinding stone in there. And what I have to do is get a smooth surface. I have to remove that top surface of the concrete to do my testing. Or if I have a hard troweled finish and I don't remove that, I'm going to get a very, very high reading. Now, unlike some of the other tests, we have to do multiple test readings. The ASTM, the one that we use in the United States, says that we must use at least 10 different readings. And each reading has to be 25 millimeters apart. So if you're using that little grinding stone on a rough surface like that, you're going to have some arm muscles, because it's going to take a lot of effort to get that surface smooth enough to do your testing. So what can you determine? Well, you can use it to determine where you might have low strength. Here is an example. I have a wall here. I analyzed the wall, and these are the numbers I got. Where should I take the core? Well, if I am the contractor, I said, obviously, I want to take it right there. Or the ready-mix company. If I'm the engineer that's going to be responsible for the building, I have to take it right here, because that is where the weakest concrete is going to be. So if I have a job where I have a 30 megapascal requirement, and I core that area and I get above 30, I know the rest of the wall is okay. And that would be the area where we would need to core. And again, if that core passes, we know the rest of the wall is going to be of a higher strength. We can use it to estimate concrete strengths. But the rebound hammer has to be calibrated to the same mixture. That means it's got the same amount of rock, coarse aggregate, same amount of sand, fine aggregate, the same cements. All this, that's got to be the same. And what we would have to do is calibrate it to cores. And it says, and again, this is ASTM requirements. So what we would do is find areas within a building that has various rebound numbers. We would core it, then develop a graph and this would be an example of what we did. Let's say we're looking at the column, find where the rebars are. We grind it smooth, use the rebound hammer. I almost replaced that slide because when we're using the rebound hammer, it has to be straight. To show it at an angle, I am hopeful that when we did that, that we were, that when we took the reading, it was 90 degrees. We would then remove a core. In the United States, we follow ASTM procedure, which says we immediately, after we take the core, we wipe it dry, we put it in plastic bags. It stays in plastic bags for 5 to 7 days, and then we test it at our testing machine. And that develops our core strength. Again, this is ASTM C42 requirements. And I know you probably have similar requirements as you do it here. If we are using different aggregates, this is concrete of the same strength. The only difference is the material or the rock itself. And this is river rock. I don't know if you use river rock here, but river rock in the United States, it has a hard shell. It has been rock that's been in a stream or a river many, many thousands of years, tumbling down. Very smooth on the outside, very hard, can be soft on the inside. Because it's a hard rock, you'll get a 40. A granite rock, which is used in the southeastern United States a lot. You can see the variation of that. Limestone rock, that's the most common rock we use in the United States, 32. And if I'm using a lightweight rock, 31. All concrete of the same strength. And that's why you cannot use that graph on the back of the chart. You have to use, it has to be calibrated to the mix and the rocks that you are using. Now, if you do all your work right, it's reported in textbooks to be 70 to 95% accurate. I've done some research work on it. When I was a young engineer, I did a study, and I was comparing rebound hammer to Windsor probe, that's where you shoot a dart into the concrete, to ultrasonic, where you put a sound wave through the concrete. I had just learned how to use ultrasonic, and I wanted that to be the best because that was the most sophisticated and all that. I found the rebound hammer was the most accurate if you take the time to do the calibration on it. And I found it much higher than that 70 to 95. I found 80 to 95%. A very, very good indication of the strength of the concrete. Now, the rebound hammer has to be maintained. And what I find is a lot of the people that have it stored into a closet or some, maybe in their glove compartment of your truck or your car, and they only use it on an occasional basis. And thus, another reason why it does give us sometimes some very poor results. there is a test anvil, and that test anvil, that is a big piece of steel, probably weighs about 30 kilograms, and it's got a place where it holds it exactly. If you're using that, that has a value of 85 if you're using the rebound hammer. So now we have a way that we can actually calibrate it. It makes sure that it's exactly 90 degrees, and I can do a comparison of that, make sure that it is being well maintained. Why is the calibration necessary? Hammer stored with a spring. If you saw how I put this in here, this has to be under compression when it's stored. So that spring is going to be going to show wear. I had a friend of mine in Mongolia that actually broke the spring of his rebound hammer. I had to, on a trip to Mongolia, get him a spring. Never heard of that before, but the parts do wear. Operators change, and it's very important on the operating procedures of how you do this. For many of us, we're not a testing laboratory. For some of you that are contracting this, it is very important that if you're going to pay for it, that they do it right. And so that you have a procedure of how they do it. There is ASTM standards on how to do it. There's probably, in Singapore, you probably have some very similar standards on how to do it. These are some of the things. I'll quote this out of ASTM. We have to test concrete that's only 100 millimeters thick. If it's thinner than that, you get what I would call the diving board effect. If I hit it, it's going to spring, if it's a very thin piece of concrete. So you're going to get peculiar readings. You got to avoid all honeycombing, all soft spots. You must grind it to get a smooth surface. On some jobs that I've worked on, we'll actually use a mechanical grinder, so that, because it's such a big area that we're looking at. Not a problem here in Singapore, not a problem here where I live. You can't test frozen concrete. If you live in Mongolia, where it gets down to 50 below zero, yes, you cannot use it in the wintertime. You got to keep everything. Your testing hole has to be less than 19 millimeters from steel. You might as well say 20 millimeters. That's 3/4 of an inch, and that's why you get the funny number. Do not compare ground to unground surfaces, so you got to make sure everything is ground. You have to hold the rebar exactly perpendicular to the surface. And as you can imagine, if I'm testing down, gravity is working with me. If I'm testing up, gravity is working against me. So those numbers have to be calibrated depending on the direction you are holding your rebound hammer. You got to keep all your readings 25 millimeters apart. And the procedures we use in the United States, we take 10 readings. We discard a reading if it's more than 6 units from the average. And if you have 2 readings that vary by more than 6, you throw all the values out. You have to completely redo the test. So the idea is you got to keep it as uniform as possible. And on some of the jobs, if you have a lot of variation in the concrete, maybe you're going from load to load, and you had one load that was pretty problematic, you may not be able to use those testing methods. It has to be compared to cores. Older standards that we have in the United States said you could compare those to cylinders, or in your case, cubes. That's not what we can do now. And our procedure says, ACI 301, which is standard for concrete, it says rebound hammers may be permitted to determine uniformity and locations of areas to be cored. These methods shall not be used to evaluate in-place strength. So it says it is a useful tool. It helps you identify, but it's not the final determination of strength. Building Code 318 says it may be useful determining if low-strength concrete exists and is best for comparisons rather than qualitative measurements. And again, it is discouraging you from making a final determination from a rebound number. It is a tool, not if you're going to go into actually determining strength of concrete, you have your cubes that you took, or you need to core. These are some things I recommend that you do, and I've had people ask me to come and do rebound numbers. What they say is, I want you to come and thump my concrete, using the concrete. And I ask them, why do you want me to do this? So I spend a great deal of time trying to make sure they recognize that this is not official, this is going to be helpful for you, but make sure before you even do this that the engineer is agreeing to it. The building officials, if the owner, make sure they want you to do this and they're willing to accept those results. And make sure, what am I trying to do with the results? Again, I'm not going to go thump the concrete, do this testing, and then say the concrete meets a design requirements. And I would say the second part of that is the operator experienced. Do they actually know and have they read the standards that they're going to be doing? In the United States, are they going to use ASTM C805? Or in Singapore, are they going to use the local standards for concrete? Make sure they got a procedure that they understand. And then the last part of this is, can I safely get to the concrete? As much as I would like to look at my concrete through binoculars, if it's high up, and I've worked on some jobs that are 100 meters tall, big silos, how do you get to the concrete that's halfway down? You know, that becomes a problem. And if you're doing it from a ladder, just think about if you're working from a ladder and you're trying to push this rebound hammer in that while you got your arm hooked around the ladder. Not a very safe way to do it. I don't know if any of you have ever worked from a boat swan chair. That's where you, when we were looking at some of these silos, we had came off the top and we were sitting in a little seat, you know, with a cable, if you will, holding us, between us and falling to the ground. Well, you're going to get too much movement if that's what you're trying to do. You really have to do it from scaffolding. If it's not on the ground, you got to do it from a man lift. You got to have something solid so that you're not going to be moving and so that you're safe on it. Again, I just did a project where I was looking at some honeycomb concrete, and they put me in a man lift and they put me in a complete safety harness, tied off. I didn't think there was any possible way of me falling out, but in the United States, safety has become so critical on some of these jobs, as I know it has in many other places as well. With that, I've tried to take you through 4 pieces of equipment, quite radically different in what they do. 2 of them are really very important as we are talking about the construction aspect of it. The infrared, be able to determine temperature, kind of the construction manual, for, if you will. That's very, very helpful for us. The second 2, the rebar locator and the rebound hammer, really are tied together, and they're more for investigating concrete after it's been placed. So both of them can be very helpful for you. What I'm going to do, I'm going to show you the computer program that we've generated for you on the plastic shrinkage cracking. Again, I'm going to leave copies of this. I got to do that though from my computer. I also got to find my glasses so I can actually see. This is what the computer program looks like. And it's an interactive program. And I'm going to ask, I'm going to put in first a problem that we might have in Arizona. Let's say we got a 45 air temperature, concrete temperature. Okay, put it, whoops. 45. You can see I mistyped it and it told me I made a mistake. Concrete temperature, let's say it is 38 degrees. Humidity, 10%. Come on. I think 38. Humidity, 10%. And wind velocity, let's make it 28. I submit that. This is designed like a traffic light. So the red tells me I'm in trouble. And this particular one, the number I had to be below was what, point or 1. I'm at 3. So what can I do? Well, if I go down here, whoop, I'm going to have to re-enter it again. 45, 38. And what was the wind temperature, or wind? 20? What did 22? Okay, if I go down here, let's see what if I have, want to wait for a better day. It says I'm not going to get there. Let's say if I lower the concrete temperature. See, it turned to green. I got to get the concrete temperature down to 11. Is that going to happen? Yeah, if with ice, I could probably drop the temperature about 8 Celsius. There are some cases in the United States where we use liquid nitrogen. We've used that on a lot of mass concrete construction. Very, very expensive, can be done. Let's see what other options I might have. We got a 22 mile an hour wind. Let's go back to our original submittal, and let's see if we just wait for the wind to die down. Yeah, if the wind is down below 1, we're okay. So we got to wait for a very, very almost windless day. Can happen. Again, I was working with a company that was having all sorts of problems like this. They were doing the 4th floor of a parking structure. And what we did is we took, because the columns were sticking up, we put plastic around the columns, they fogged it, using where they put a lot of moisture in there. The plastic kept the wind off it, and kept the moisture from being blown away. And the moisture also lowered the temperature. One of the very common ways that we are outside dining, if you will, in our area, because it's so dry, we just put moisture in the air. If you're in Singapore, you put moisture in the air, you just make it more uncomfortable. But in a very dry climate, that is a good way of cooling people down. Again, you got, this is available to you. I think I just showed you some ideas of how to use it. If you want, we can put in some local conditions. We can do that afterwards. That, ladies and gentlemen, is our presentation that I have. And what I would like to do is have you come up here. We'll stop the formal part of this. Have you come up here, see the tools. I'll be up here. Kurt will be up here as well. He can help you on some of the metal locators. Kurt, the fellow that's running the camera right now, is with Zircon, which makes one of the pieces of equipment. And so he can help us as well on this part. So with that, come on down and we'll take a look at the equipment. Thank you very much.